of load current. Notice that the local breaker X closes first, and the remote breaker Y closes about 2 cycles later. During this period, the line is energized from one end only. The small current flowing is due to line charging. After the remote breaker closes, load current again flows. Number 4, only the faulted line has tripped. We can tell this from the received carrier signals on lines 1 and 2. Since this is a carrier blocking scheme, a received signal means that high-speed tripping is blocked. You can see that the system operated correctly. The unfaulted line 2 breaker receives a blocking signal, while the faulted line 1 breakers receive no signal. This allows line 1 breakers to trip at high speed and clear the fault. This example has demonstrated a case where the protection system worked exactly as we expected. The role of the oscillograms was to confirm this fact. Here's an example of how oscillograms, along with some computer simulations, can help pinpoint the location of trouble areas along a transmission line. The system one-line diagram shows 2 substations, A and B, separated by 100 miles of line. Both stations are equipped with oscillographs that monitor transformer neutral currents INA and INB. This installation suffers a particular problem. The line trips and recloses on a recurring basis. The faults seem to occur whenever the line is heavily loaded and wind velocities are above normal. This leads us to believe that the line is sagging under heavy load and making tree contact. But we have no idea where the problem is located. We can prepare for our investigation by first running a series of simulations using a short-circuit computer program. First, we assume that a fault occurs at various points along the line, say 20 miles, 40 miles, 60 miles, and 80 miles. For each different location, the computer program calculates a ratio, INA divided by the sum of INA and INB. This ratio represents the fault current contribution from station A divided by the total fault current. When the fault current ratio is plotted against fault location in miles, we get a series of points and a curve that looks like this. If the fault is very close to station A, INB will be quite small compared to INA, so the ratio will be close to 1. On the other hand, if the fault is close to station B, INA will be small and the ratio will be close to 0. For a fault near the middle of the line, INA and INB will be about the same, so our ratio is close to 1/2. Of course, we can create a whole family of curves for different system conditions, such as maximum generation and partial generation. Now that we have the simulation curve, how are the oscillograms used? Well, after a fault occurs on the line, the oscillograms are checked, and the magnitude of neutral current in each station is read from the plots. For this particular fault, INA is 1,500 amps, while INB is 4,000 amps. Our fault current ratio is 1,500 divided by 5,500. This works out to be 0.27. Now, going back to our computer simulations, we can select the curve that most closely matches system conditions at the time of the fault. The ratio of 0.27 corresponds to a line length of about 75 miles. Thus, we conclude that the trouble spot is approximately 75 miles along the line from station A to station B. In this particular case, a foot patrol located the probable tree contact within a mile of the calculated distance. The problem of recurring tripping of the line was solved by tree trimming. Incidentally, some utilities use fault locators which are programmed to perform the calculations and then give us the exact distance to the fault. Okay, in this segment we have shown a couple of examples of how valuable oscillograms can be in a fault investigation. In the next two segments, we'll consider some actual case histories of faults and how they were investigated. At this time, switch off the videotape, study this material in your workbook. Hello again. In previous segments, we introduced you to the basic tools and techniques used in fault analysis. And now, let's tie all this information together by looking at some real-life case histories. We've already examined a case where a line tripped out of service and reclosed successfully. Now let's consider case one, an unsuccessful line reclosure. In practice, this happens quite frequently when the line does not stay de-energized long enough for a temporary fault to clear on its own. In this example, the oscillograph has captured the substation bus voltages in all three phases, the transformer neutral current, and line current for one of the transmission lines. The oscillograph system in use here can record 3 cycles of pre-fault data. From the trace of line current, you can see that the line we have monitored is not the faulted line. This is obvious since the current resumes its normal load level after the fault is cleared. From the bus voltages, we conclude that the fault is a single line-to-ground fault on A phase. This is confirmed by the transformer neutral current. We can also tell that the fault duration is 4 cycles, and the line dead time is 11 cycles. At this point, the breakers on the faulted line reclosed, but the fault was still there. So the breakers immediately tripped out again and locked out. If this problem repeats itself over a period of time, we may conclude that 11 cycles of dead time is not enough to allow the temporary fault to deionize and dissipate. In this case, the dead time would be increased by changing the time delay at the breaker. Our next case history, case 2, shows what happens when the nature of the fault itself changes during the disturbance. Here we have a fairly extensive 69 kV subtransmission system that experiences a fault on the tie line between substations Y and Z. The 69 kV system is delta connected, but effectively grounded through zigzag grounding transformers located at substation X. Notice that all the oscillograph equipment is installed in substation X, remote from the fault location. In spite of this distance, we can still obtain a great deal of information from the recordings. The oscillograph has recorded 69 kV